This is the conference for the C++ community. Here we get to discuss with the standards community and with all of the innovators that are building C++ now and for the future, the innovations and opportunities that we have in our company, as well as the opportunities that they're exploring as an industry.
Welcome to this installment of the software design track. We're going to talk about design patterns and some of the misconceptions. So before we get started, allow me to quickly introduce myself. I'm Klaus, and you might have heard about me because I'm the guy who talks about software design and design patterns. Why? Well, probably because almost nobody else does, and somebody has to. And so I've read the book about software design. I organize a unit user group, the C+ user group, of course, and do various things at conferences. So this is the second of two talks. Curiously enough, I've not done the first version at CppCon. That is because last year, for the first time, there was the rule that every speaker can only give one talk, and so I did one for the Back to Basics track. But this year, finally, I can actually talk about design again. So in the first version, I talked about 4 terms, both at NDC Tech Town, but also at Meeting C++, in case you want to refer to that later. So I talked about builders, factory methods, bridge, and design patterns in general, primarily about terms. And so today, I definitely want to talk about design patterns again, but I have chosen something slightly different. Today, I want to talk about virtual functions. And boy, this is a fantastic topic, isn't it? Because this is one of the things that we can have ultimate dispute in the community. So for instance, 2 years ago, Ivica Bogoslavievich talked about the hidden performance price of virtual functions, essentially telling us that virtual functions are slow. He didn't really say that they are slow and you should avoid them. Okay, this is one of these talks that tell you avoid them. But then the year after, Sasha actually talked about optimizing virtual functions may be pointless. Wow, and now I'm super proud to actually chime into this battle, but from a slightly different point of view. I want to take a look at this a little more from a design perspective. So I will talk about 2 details, 2 things. I'm going to talk about CRTP, yes, one of our most beloved abbreviations, and I'm going to talk about stud variant specifically. Good, so let's jump right into CRTP. Now, I guess many of you know CRTP, have heard about this before, but of course there's the chance that some people have not heard about this before. So this is a pattern described in 1995 in a paper by James Copeland, in which he basically just reported that there is an interesting template-based pattern that many people have used in their code bases. And he found this to be truly curious, and so he wrote a paper, Curiously Recurring Template Patterns. He didn't really name the thing in the paper, but the name of the paper then turned up to be the name. So this was not really consciously chosen, but okay, we name it CRTP today. So what is CRTP? Well, imagine you have an inheritance hierarchy. And I'm going to choose a classic one. So say we have an animal-based class and a sheep-derived class. Now, the base class, first of all, is a class template. And now here comes the curious part already. The derived class inherits from this base class by passing itself as a template parameter. Whoa. So if you have seen this before, you now know and say, yeah, Klaus, move on. But if you have not seen this before, this is truly curious. Does this even work? Oh, it actually does, because as soon as you say class sheep, you have kind of full declared the thing, and you are allowed to instantiate class templates with incomplete types. So it actually does work perfectly. But now, of course, animal is a base class for sheep. But what we want to avoid here is virtual functions. So the first thing that we now do, one step back, we usually call this template parameter derived, which is actually a good thing because this might communicate to people who have not seen this before what you're actually doing. So I would say this is kind of part of the pattern. So now, in the base class, we default the default constructor and the destructor. The destructor in particular because, well, it should not be virtual, but it is a private destructor. Now, of course, The derived class cannot access this, so we befriend the derived class. This actually might help. Sometimes, due to typos, you might use a different derived type here, but then it would not compile. So it's a little bit of protection and truly recommended. So in the derived class, you will not really have to do anything special. Do not mention the destructors. Remember the rule of 5. Leave it away. So now, in a base class, of course, we have the functionality that all of the derived classes should have. Yeah, it's an interface. It's an abstraction of animals. So let's say that we want to have a make sound function. But in a base class, I have no idea what I want to do. So it's an interface only. The real implementation, of course, is in the derived class. But now, it's not a virtual function. So how do you get from the base to the derived? So I do a static cast on myself. So I statically cast this to the type of derived, which is perfectly okay because derived is an animal. So this is a perfectly legit conversion. And on that thing, the derived type, I call make sound. Pretty cool, isn't it? Pretty cool indeed. So, and indeed, I can now use this, say in a print function, when I print an animal, I can print the animal, can call make sound, and this will not trigger any virtual call. There is no virtual function. And functions might even be inlined. So it's absolutely amazingly fast. Fast indeed. And so now, again, if you've seen this before, you're not, yeah, I know. But if you've not seen this before, oh, I know the reaction. Big eyes. Whoa! Seriously? That's the holy grail of inheritance. Klaus, I am only learning about this today. And you're making big plans. Next week, after CppCon, of course, you're rewriting your entire code base. Yeah, of course, you get rid of the inheritance hierarchies. You replace this with CRTP. Now, before you make any big plans, please don't. Pretty please. So before we now move on, I actually should talk about the two kind of obvious disadvantages that you might get. And if afterwards you say, okay, this doesn't bother me, then you might start some refactoring. So limitation number 1, every derived type has a different base class. Now this needs a second to sink in, and I even say it again. Every derived type has a different base class, which is not what we usually want to have in inheritance hierarchies. So you cannot simply have a vector of animals. There is no such common type, such a common base class anymore. So, no, this is not a replacement for this kind of inheritance hierarchy. Okay, this may already be a pretty bad limitation, but there's one more thing. I've shown this slide before, and I've said, well, now we can use all the animals in the print function. But now, watch closely, that the print function is a function template, which of course makes perfect sense because, well, the animal base class is a class template. So now you're thinking, now what? That seems to be reasonable. Okay, if you now use this everywhere in your code, if you use a lot of CRTP base classes, everything that comes into touch with its base class is itself a template, function template or a class template. And this truly acts like a virus. So if you use this everywhere, well, all your functionality moves from the source files into the header files. And slowly but steadily, you end up with, exactly, a template header-only library. Okay, and I guess that you now realize this might not be the thing that you want to end up with. And so no, it's not really a replacement for in every possible inheritance hierarchy. However, perhaps there's something else. So at CppCon 2021, Ben Dean talked about the deducing this pattern, aka explicit object parameters, what the feature is truly called. And in his talk, he showed that CRTP can actually be replaced by something far simpler since C++ 23. So let's take a look at the example from that slide. So say we have some numerical functions base class. Yeah, and you see it's a CRTP base class, immediately visible because of the derived template parameter. And this class comes with a scale function. We convert ourselves, again, same pattern, to the underlying type. And on this underlying, we call some set value and some get value functions. Now, sensitivity derives from numerical functions of sensitivity. That's the pattern again. And now provides get value and set value. And so now we kind of inject the scale function into sensitivity and can use it, for instance, here in a main function. So sensitivity is created and we call scale. And this works perfectly. However, now we can simplify this, perhaps improve it by means of an explicit object parameter. So in the scale function, we use one of these explicit object parameters. This autoref here, that's the type of the this object, introduced with this. So we now deduce the type of the this object. We still inherit from numerical functions, but note, no template parameters anywhere anymore. No templates. We still inject the scale function, but now if it is called here, it actually still works. So we can now deduce the type of this derived class. Whoa, that is cool, isn't it? Oh, it really is. And so a lot of people jumped on the train and said, well, we can do better. We can actually replace CRTP with explicit object parameters. So Ben himself in his talk said, well, so CRTP really just, I guess, goes away. And so I saw this talk last year where this was just presented as simpler. Also this one, in this talk by Timo Dumler at NDC Tech Town, he just said, well, we can do better with C++23. Good. However, let's take a closer look at their example. Again, I've tried my best to get the gist into the animal shape example. So I have this animal base class with a make sound function. Now this time, I deduce self. Oh, this is wrong. Ignore this. So I call a make sound impl on the derived class. And in the derived class, I provide the encoding function. Good. Now I create a sheep. I might assign this to a referenced animal. After all, it's a base class. On sheep, I call make sound. Works. I call make sound an animal, and it doesn't compile. This actually happened in a lot of talks in the last years. I know at least 3 of them. I suspect there was a 4th one. A lot of people presented code that actually wouldn't compile in their talks. That was strange, curious. I think this was actually I think all these people were victims of a little bit of a confusion. But Ben made this quite clear in his talk. In his talk, he explained that this actually could not work. Now, if you have this relationship, and if you use base and derived, only in case you call something via the derived, you can deduce the type of the derived. But if you call something here base, you cannot derive the type or deduce the type of the derived object. It just doesn't work. You can only deduce the static type of the object, not the dynamic one. However, well, Ben said CRTP. And unfortunately, some people thought about CRTP, perhaps in a slightly different way. So on his slide, Ben also provided a link to Fluent CPP. On Fluent CPP, a couple of years ago, Jonathan Pocara actually explained these 2 different kinds of CRTP. So let's take a look at the middle paragraph. There are several ways the CRTP can be useful. Here I'm presenting the one that I see most in code, adding functionality, and another one that is interesting, but I don't encounter as often, creating static interfaces. So, 2 forms of CRTP. Okay. What are these two forms? So remember the example with the numerical functions base class and the sensitivity derived class. In this context, the numerical functions class provides something that I inject into the derived class. Some injected functionality. And I use the thing via the derived class. I don't really bother about numerical functions. Sensitivity is the thing that I use. In that context, I can very easily use an explicit object parameter. This works, because at this line, I will deduce the type of the derived object. This works, this is good. Unfortunately, the other example, it is a little different. So I'm using the makeSound function via the base type. But the base type, it simply cannot, so here's still the CRTP form. In CRTP, I can definitely go to the derived class. I know that because of the template parameter. But with explicit object parameters, again, ignore this here, it just does not work. I cannot deduce the static type, the dynamic type, only the static one. And so, this cannot be replaced by explicit object parameters. But now you see, it's confusing. It is confusing because there are two forms of CRTP. And if I now tell you, I would use CRTP for that, you might actually think about exactly the opposite thing. There's an obvious potential for misunderstanding. The term is ambiguous. And so, obviously, this leads to misunderstandings. We need new terms. So, but now before adding anything or suggesting anything, I apologize. Yes, I apologize. I could have had the chance. So in my book, actually, I wrote about the CRTP. I introduced both forms, but I did not introduce any new terms. Although it's a book on design and on terms. That is bad. So I messed up. As I said, I apologize. But now perhaps this is the opportunity to do better. So if you use CRTP for static interfaces, then first you use this because you want to have a base class for a related set of types, a family of types. And you want to define a common interface. This is the operations that all of my types have, all of the derived classes. So I really use this via the base interface. And this means, in this context, you are introducing some kind of abstraction. So it's a design pattern, a pattern that you use to create an abstraction. And so I suggest that we call this form of CRTP static interface, just like Jonathan Bukhara has done a couple of years ago. I think this is fitting. This works. And it's unambiguous. So if you talk to somebody and say, I would use a static interface for that, this somebody now cannot say, I know exactly what you're talking about. If you want to add functionality, though, if you want to inject some function, some code into another class, it's a different application. So you create this base class as an implementation detail. This is not a common interface. This is not something that you that defines what operations are always available for a family of types. And so you also don't use it via the base interface. So you do not introduce an abstraction. It is, after all, just an implementation detail. So this is what I would call a mix-in, just like so many people have done before us. Mix-in is a common term and good, well-known term for this kind of design. However, it's not a design pattern. It's an implementation detail after all, and so it's really different. And so now, I think these two terms might simplify things and avoid the confusion in the future. And so nobody should present any example anymore that actually doesn't compile. Good. So, to summarize here, to prefer the term static interface to express the intent to create a static family of types. Good. And static interface is a design pattern. Because explicit object parameters are an implementation detail, it just cannot replace that. It's different. And prefer the term mix-in to express the intent to inherit implementation details from a base class. So, Mixins are an implementation detail. So in that context, explicit object primitives can help. They are an alternative because also here it's an implementation detail, and so they can replace CRTP. And so perhaps still there's a little CRTP around after all. So, but now, at least one of you cries out, wait a second, Klaus. I'm not entirely convinced about what you're saying here. I think we can even replace CRTP with something else. Look here, I have a suggestion. Can we just replace CRTP, the static interface form, with the C++20 concept? Interesting suggestion. And so perhaps you're thinking about the following idea. So you would have a concept that defines what an animal does and is. So our animal, again, has a make sound function. All right, then we would have the print function from before. That would just take a t, but this t is now constrained to be an animal. So we could call make sound on the animal, and this would work. And sheep would not have to derive from anything. Sheep would just be a sheep, and we could print the sheep. Now it fulfills all the requirements of the print function. That's it, right? Ha! CRTP is a goner. Okay. Now I'm not convinced about this. What can I pass to print? Well, of course, anything that fulfills the animal concept, right? So, what about this guy? Yeah, I can be printed too. Me too. It is logical to assume that I can be printed too. So, you know what I'm trying to say here? This is what we call duck typing. Okay, might have been obvious. So, this is just a give me anything that fulfills this idea, this concept. But no, this is not what CRTP is for. In CRTP, you define a family of types. A family that you opt in explicitly, which you usually in real life might not be able to do, but in here, in code, it is possible. And you want to have a set of types that you can control. So that is not a replacement for CP. This is something else. However, we might still make it work. We now just have to do something that is an opt-in, something that is explicit. And that might be something like an animal tag base class, a simple base class. Now, an empty class that now I require sheep to derive from. In this concept, I now simply also require that the given type derives from animal tag. And if it does, it is one of the types that we count as animal. That is explicit. This is opt-in. So this might truly be a replacement for CRTP. I cannot be printed anymore. Me neither. And it's logical to assume that now I'm unprintable as well. Okay. Now, whether this is better or not, it's up to you. This is perhaps a little more modern, perhaps also from a compile time perspective, not bad. Concepts are quick. However, this CRTP base class definitely has an advantage too. It's a base class. It very nicely expresses the intent. Here is the set of common operations. Okay, so you will have to wait, pros and cons, but this is kind of the same as CRTP. So I should add one more thing, and I explicitly use a base class. You have to do something that cannot just happen by coincidence. Oh, coincidentally, somebody had this data member. No. It must be something that you explicitly do, or it's not an animal. And so base class might just be the right thing for this purpose. So, yeah, same summary. However, perhaps in the end, you can replace all kinds of CRTP by something else. But it is different. So please remember the two terms, static interface and mixins. Good. All right, so much for CRTP. Let's turn our attention to some other topic that is pretty dear to my heart, stirred variant. Performance, right? Okay, but before we talk about that, perhaps a little bit of, say, a code scenario. Yeah, I'm using the same thing again that I've used so many times. And I know it's boring, it's definitely not rocket science, but it's simple. It's so simple that I can now throw a couple of, say, 200 lines of code on the slide, and you probably still have an idea what is going on. That's important. So we are going to draw shapes again, but this time I now specifically want to keep this extendable. So I want to be able to, perhaps at a later point, add rectangles and perhaps a couple of ellipses. Eventually somebody wants triangles too. That needs to be doable. So requirements, I want this to be extendable by new kinds of shapes, which I believe is reasonable. Second, we now assume that, of course, it's not just these 200, 300 lines of code that I'm showing, but it's a big code base. Yeah, please always scale this in the back of your mind to, say, 10 million lines of code. And say this is also a project that is developed by 100+ developers. So scale it up, large scale. All right, so then we might actually solve this like this. So here's a suggestion. We might start with a shape base class. So a shape base class provides me with a draw function. There are other functions as well. We're thinking about draw now, but it's a base class, there's stuff in that. Now there's deriving classes, of course, like this circle. Circle publicly inherits from this shape. For that reason, the circle now has to implement draw. It doesn't have a choice, it has to, it's a pure virtual function. But unfortunately, the circle doesn't really want to inherit from, it doesn't really implement draw because there are dependencies here. So think about a graphics library, for instance. And the circle most definitely does not want to depend on OpenGL, 3DX, or any other graphics library. It wants to be a free and simple circle. And so to manage this dependency, let's also introduce another base class called draw strategy. This draw strategy represents the implementation details of drawing. And the circle just takes one of these draw strategies in the constructor. So it gets this with a unique pointer to draw strategy. Circle moves this into its data member, and from now on knows how to draw itself. It doesn't have to know anything about the implementation details. It's not free of this, but it can still draw itself. Great. Yeah, this is a design pattern, the strategy design pattern. Now, of course, the circle is a little alone, so there's also a square, but this is the same thing again. Also, the square would take a draw strategy, now one for square, and it would draw itself by means of this draw strategy. Good. All right. Now, of course, I want to have many, many shapes, so I introduce a vector of unique pointers of shape. Pointers to shape, it's a base class, so we store things via pointers. Good. And now I need a vector of shapes. Many circles, squares, and of course, potentially a few others. How do you get one of those? Well, of course, with a factory. Now it's getting fun, right? A shapes factory. The shapes factory is an interface to create some shapes, an entire vector of shapes, say from a file. I read everything in from this file. And then I want to draw all the shapes. So the draw all shapes function takes one of these vectors, one of these many shapes, just traverses all of them and draws them. Reasonably simple. And so I can create them, I can draw them. So I want to create and draw shapes. That function would take a shapes factory, it would take a file name, and it would use your factory to produce a vector and to draw all of the contained shapes. Cool. All right. Now, we want to draw something, so let's say we introduce a real implementation for this draw strategy, an OpenGL drawer. So the implementation details are not important, so there's nothing really visible. But say this is the class that really draws circles, squares, potentially other shapes. Okay. And now, of course, we also need a real factory implementation. Say this is your shape factory. Okay. Strange name, but it is yours. So you would implement this create function, and now you don't have to read the code. We just extract circles, but also squares from the file, create them, set them up, put them in a vector, and return the vector. Nice. And so, finally, I can now create a factory, call, create, and draw shapes, and see a couple of beautifully drawn shapes on the screen. Yay! Great. So, however, I said initially that I also want to make this extendable, keep it extendable. And so let's do something that's pretty important. Let's actually separate concerns. So let's separate your code from my code. And so I now draw a line, an architectural boundary. Above this line is my code. That's the high-level code. I'll consider it's a little more stable, perhaps. These things will not change so often. And below this line is your code, the low level. Okay, but know what? High, low level, this is always confusing. Let's simplify this. Let's just say this is my code, this is your code. Okay, so you want a rectangle. And you can add one, quite simple. You can introduce a rectangle. Again, you don't have to read the entire code. It's the same stuff again. The rectangle would take a draw strategy, now for rectangle, and it would draw itself via the given strategy. Great. In your code, you would also extend the OpenGL drawer. It's your code after all. You've chosen OpenGL. And you would also extend the shapes factory accordingly. So there's a new case. This is a rectangle. You would extract a rectangle from the file. Good. So, and we can still draw this thing, create and draw the thing in the same way. Nice. So it works. Thumbs up. You're a tough crowd, you know that? Really? I thought this makes you happy. It works. You look. Thank you. But seriously, many of you look very skeptical. Very skeptical. And I kind of have a suspicion why. You're a little unhappy about the style of programming, aren't you? The style of programming. The style that we today refer to as the Gang of Four style, based on this book, the Gang of Four book, the GOF style. This book, okay, it is from 30 years ago. And indeed, in December this year, it was released 30 years ago. That's the book that basically says inheritance and virtual functions are the answer. But then at the same time, you might also remember this talk. In case you do not remember, that is something that you can watch this evening. Yeah, after all the CPP talks here at CppCon that you see, you watch another one online, and it's a short one only, 24 minutes. John actually had only 20 minutes, but used 24 of them. Inheritance is the base class of evil. So, that's a pretty strong title. It's a funny one also, I admit. But that kind of says a lot. Inheritance is bad. And today, I think this is in the minds of many people. Inheritance is not good anymore. And so, 2 years ago, at CppCon 2022, there was a talk that kind of made this quite explicit also. Using model C++ to eliminate virtual functions. Okay. I know, this sounds kind of a little aggressive, eliminate virtual functions, but it kind of carries the same philosophy. Virtual functions are bad, slow. Okay. I also got a review to one of my talks, I think it was also approximately 2 years ago, a review by somebody I do not know, and so I can just say this is an unknown review. So this is what I got. I believe that object-oriented programming, and especially its theory, is overestimated. C++ always had templates, and now also has stood variant, which makes most of the use of inheritance unnecessary. Of course, stood variant. That's it, right? That's the solution. No inheritance, a little container that can just store different kinds of things. That's it. So let's improve the code. Let's modernize the code. Let's implement everything by means of stood variant. So we're going to start by just writing a circle. Note, There's no base class. We also write a square. There's no base class. In fact, there's no inheritance at all. So consequently, there's also no virtual function, etc., etc. You also don't see any strategy, no unit pointed to some base that tells the square and the circle what to do. No, this is pretty much a pretty primitive square class, a geometric primitive. So I do not depend on any graphics code, not even implicitly. There's no pointers to base, there's no manual lifetime management, and there's just less code to write. Great! And now here, the first variant. Our variant now stores either a circle or a square, and perhaps later a few more. So that's an abstraction of a shape, hence the name. This is now a shape. Nice, nice, good. Then, I don't need pointers anymore to store different kinds of things. I can have a vector of variance, a vector of shape, which even from a language perspective is so much more beautiful. What are many shapes? Well, a collection of shape objects. Great, ha, I like that. Good, then we can create these things again. Again, we have a shapes factory. It's pretty much the same code, but the one thing to note is there's no base class. I don't need a base class. I don't need any virtual functions. I can totally go without. And you also note, I do not allocate circles or squares or rectangles. I just create them. I create a circle with some radius and put them in the vector of variance. Nice. Nice. That's simple. That's intuitive. Great. I like this. Oh, and here's a second opportunity to abstract. A factory is, well, a variant of shapes factory. At this point, there's just one, I know, but imagine, of course, there could be many more. Different ways how you can create shapes from files, other things, database, etc. Nice. Good. Then, of course, eventually we want to draw. So we have our OpenGL drawer again. It's one of many others. But again, note, there's no base class, no virtual function. And again, a little less code, it's simpler and just more beautiful, right? And here, the third opportunity to do some abstraction, a drawer. A drawer is just an abstraction of different kinds of drawers with OpenGL, 3DX, or whatever. Ooh. And now, you've not even seen the best of it. Draw all shapes. Draw all shapes now visits some shape. And you know what? I now pass two variants to this visit. Yes, two abstract things, a drawer and a shape. This is multi-dispatch. Yeah, actually, C++ as a language doesn't really support multi-dispatch, but this is still multi-dispatch. Pretty cool. Yeah, I see you're warming up to the idea. Great. And then we have, of course, another visit in the create and draw shapes function. This one creates a vector of shapes again and calls and draw all shapes with this. Nice. In the main function, I create a factory, I create a drawer, pass this to the create and draw shapes function, and again, this just works. Wow. So much better, isn't it? So much better. And now I totally understand why you do not react. You're totally speechless. You don't know what to say. Klaus, this is so much better. So much better indeed. No inheritance, but a more functional approach. No smart pointers, no pointers at all, but values, value semantics. Proper management of graphics code. There's no coupling. This is just two things that I bring together at one point. Great. It's automatic and elegant lifetime management. You do not have to use smart pointers for that. And so it's simpler, less code to write for you. Great. And so much simpler. But you know what? There's one more point. You're gonna love it. It's even faster. Performance. Although, I now know what I've just done. I've again mentioned the one word that piques everybody. Now everybody's awake again. Performance. Whew. Now that's the one thing that is a little tricky to do, because as soon as I now show performance results, again, I'm gonna get a lot of emails. Klaus, I'm gonna have different results in my machine. Klaus, I'm not agreeing with the performance result. It always happens. So, yep, I'm gonna show you a couple of performance results, but you will have to promise me that you will not complain about them, that you just take them as some results that I came up with. So, do you promise that you will not complain later, that you will not send me an email about this? And not even after the conference. So, if you're watching the video, no, I do not want to see any emails. Good. But I do believe that most people have agreed, and else I will just not reply. Here are the performance results. My performance results. And I should say, indeed, this is just mine for a specific set of, a specific scenario. I have 6 different kinds of shapes: circles, squares, ellipses, rectangles, hexagons, and pentagons. And please do not believe that I took a lot of time to implement a full-fledged hexagon. It's an equal-sided hexagon only. I'm using 10,000 randomly generated shapes. Randomly generated is supposed to let the compiler not optimize too much. I want this to be realistic. And I'm doing 25,000 translate operations. Okay. I'm not drawing. I'm doing something that is the same on all the shapes, which a compiler cannot know, but it's the same amount of work for every kind of shape. And it's a very, very cheap operation in itself. So cheap that really we can see a difference in the different approaches we use. And so from a compilation point of view, I used UCC 13.2 and Clang 18.1.4, and a not quite new machine anymore, but that shouldn't be a problem. Good. So here are the results. Classic object-oriented programming, the thing that I've shown you first, has this performance. Okay, it's a number. And now it's also not a race between GC and Clang. That doesn't matter at all. Std variant, better. Okay, now people will complain that I treated Clang unfairly, so I owed you through an impact variant, which looks even better. Whoa. And now you're totally convinced. Twice as fast! I'm buying this. On next week, so on Monday, I'm rewriting all the inheritance hierarchies with Std variant. Please don't do this either. It's a terrible idea. And so perhaps we should now talk about that part. So you might be happy about the simplicity, and I totally agree. This is simpler, this is more straightforward. But if you now analyze design again, you might find this is not great. So again, let's just separate our codes, your code and my code. Draw shapes and create and shapes, this is my stuff, for sure. So I think we should put the line here first. So my code, your code. Okay, doesn't look right at the moment because, of course, you should decide how to draw, OpenGL, etc. And you should have factories, etc. Okay, so the OpenGL drawer, that's your code. Okay. We just have to rearrange stuff, so the OpenGL drawer goes into your code. Fine. There, wait a second. That using drawer at the bottom, that is not your code, right? This is my abstraction. Okay. Again, just a little rearrangement, so I put this up into my code again, because I need it. Yeah, you just seen this. I need this abstraction in my code. Good. But oh no, wait. The OpenGL drawer is your code. That actually means that I now still have to know about your code. Okay. And so what I'm now trying to say here is, it just doesn't work. It doesn't work in the way we actually want to extend our library. This is not really what we want to have. So this is an architectural disaster. It is a failure from an architectural point of view. We cannot really work together anymore. I cannot have the interface stuff, the stable stuff, and you cannot extend it. And that is simply because there is no architecture. All of this now is one thing that belongs together. There's just one level, there are not two anymore. Okay. But going back to this little review, there's one more term that makes the difference, perhaps. C++ always had templates. Of course, we can save the day by just throwing in a couple more templates, right? So let's just do that. Okay, so draw all shapes. Draw all shapes is now a function template. The type of the abstraction, the type of the variant now is just a template parameter. I'll still visit with this thing, this thing needs to be a vector of, the vector of drawers, whatever, but it's now a template parameter. Same for the create and draw shapes. Again, draw needs to be a variance thing. Okay, that's gonna help. Indeed. So now if we do this and that, forgot the animation, then actually the shape abstraction can be on your side. You decide what you want to define as a variant. It's yours. And you can definitely define this shapes factory. Also the rectangle. You can introduce a new rectangle if you want one. Why not? I don't care about this, but you might. And you can, because the abstraction is on your side, also just change the abstraction. Great. That is working. Good. You can extend your shapes factory, you can extend your drawer. It's all on your side of the architecture. Nice. Suddenly it's working. I'm not convinced though. I'm not convinced though that this is the final, or should be the final solution. Remember what I said when we talked about CRTP, that it's a little bit like a virus? If we now kind of do the same thing here, yes, of course, we do end up with a lot of header files, a lot of templates, and in the end, this might truly be a header-only template library again. And is this truly what you want to have in a 10 million lines of code base? Probably not. So what we've just done is we've kind of repaired all of this, the failure, the architectural failure of state variant, but just thrown in another kind of abstraction. The templates now serve an abstraction, but it's a totally different one with a very different purpose. You cannot just do that. They're not equivalent. So state variant is not a silver bullet. It's not the one solution that helps us to make code more modern or faster. No, and most specifically, now with underlining, state variant is not a replacement for virtual functions. On the contrary, it's the opposite. State variant is the architectural antipode of virtual functions. So if you compare these two quite quickly, then first of all, I should mention that both are dynamic polymorphism. Also in the past 2 years, I've seen so many abstracts, people saying state variant, putting state variant in the static polymorphism regime. That was strange. So let it be said, both is dynamic polymorphism. But the state variant has more a functional approach. Virtual functions, of course, are more the object-oriented side of things. But this is the difference that really counts. Because the state variant is something where you have a fixed set of types, whereas the virtual functions enable you or give you an open set of types. I can introduce new types in an object-oriented setting super easily. I cannot do this with a state variant. But then for objects, for operations, it's just the other way around. For state variant, you can write new operations that you can just apply via state visit. So you have an open set of operations, but cannot just add a virtual function to some abstraction that you don't have the control over. So it's a closed set of operations. So they're very different. And so both of them have architectural properties. In particular, the state variant has the properties of what we commonly call the visitor design pattern. A very specific architectural solution, a specific design. And so please, do not consider studvariant as a replacement for virtual functions, and please don't use it as such. This is just not okay, not correct. But then again, somebody cries, wait, Klaus. But Jean Parent, remember Jean Parent? He told us that inheritance is not okay. And now you are telling us that variant is not okay. So now I'm confused. What should I do? Okay. So as much as I like this talk, it has one problem. The title kind of suggests that Jean Parent says that you should not use inheritance. But do watch the talk or watch it again. The final solution actually does use inheritance very much. And so this is not a talk that tells you inheritance is bad, you should avoid it. No, it's a talk, as so many others from Jean Parent, about value versus reference semantics. That is what he really is concerned about, values. And so the solution that he presents is a solution more in the object-oriented regime. We can add no types quite easily. So, however, to quickly summarize these two, because I've now put them together because they are usually seen as some kind of replacement for virtual functions. Neither CRTP nor studvariant should be seen as such. Pretty please. Design patterns in general represent a dependency structure. This is why we have so many names for them. And every name that we use for a design pattern, visitor, strategy, and the like, represents such a dependency structure. And so, of course, these design patterns have architecture properties, a dependency structure. And therefore, you cannot just replace one pattern with another one without any changes in your code base. Not just the coding changes, but an architectural change. And so, no, that just doesn't work. So, think about your design architecture first, and then about the implementation details. So what kind of design, what kind of architecture do you want? What do you want to extend or not? And then, after you've chosen an architecture, a design, then think about which pattern, which kind of abstraction fits your design. And please don't design based on performance requirements. I mean, of course, sometimes perhaps it's necessary, but it shouldn't be. And so, I think this is a pretty important mindset for the big code bases. This is where it really starts to matter. And so, I want to end with saying architecture and design first. Thank you very much. All right, we might have a few minutes for questions, in case you have any. Else, please.
Hi, my question is more about like seems to me what you just showed us is similar to the well-known like expression problem. Like you either like your design either hard to add new types or hard to add new functionality. So
yep.
So like I actually like this talk is very helpful because I actually encountered a similar situation during my work like last week before I came to CppCon, and my colleague is using the ST-variant solution, but then we realized we want to be able to add types easily, so we changed it to like using integers.
Good. Yeah. So do not choose variant because it's beautiful and simple. Choose it because it architecturally fits your design.
Yeah.
Good.
Thank you for the talk. It was very interesting.
And you do not complain about performance, right? No, okay, then you're good to go.
Yeah, no complaints, no complaints. I did have a question though. I've always been, I think variant has a lot of really cool use cases. I have always been a little bit suspicious of this kind of use case. But one thing that I am curious about was whether or not in the benchmarking you had tried more types with the variant, because I would expect that the dispatch performance of variant would decrease as you increase the number of types that can be in the variant. Whereas I would expect that the virtual function would be kind of static. So like
Correct.
I would expect that graph could start to invert itself and
Correct.
really start to scale up.
With many, many types, I did not benchmark from which number on this happens. No idea.
Okay.
And of course, it again depends on the implementation, the compiler, and so many factors, but you're right. The virtual dispatch has a fixed cost, but the dispatch that the variant does must have a linear cost.
Yeah. Thank you.
Thanks. Not complaining about performance, but asking about it.
I knew it.
No.
Did you raise your hand?
Let's not talk about that. Yeah, in your figures, I was just wondering about the difference between GCC and Clang. Was that exclusively about like the compiler, or did you have a different standard library implementation, or what?
Yes.
So
absolutely.
Libs to C++ versus Libs.
Exactly. Yep.
Right.
And of course, I did not take a look why this is not the point of this talk. Yep.
I still found that interesting.
Okay.
Thanks.
So.
Hi. So can you go back to the slide where we have the table comparing the city variant versus the inheritance setup?
This one.
Yes. So thanks very much for the talk. It was amazing. I was imagining you would close with perhaps a third column here that would have a hybrid that maybe is the best of both worlds.
Okay, I get the question. If you are in dynamic polymorphism, so if you stick to dynamic, there is no third column where you can combine both of these easily, where you can add types and operations easily. From my point of view, this doesn't exist, or only with horrendous costs. If this is interesting to you, take a look at the so-called acyclic visitor design pattern.
What was it?
The acyclic visitor design pattern.
Okay.
So Google for this, you'll find something. This is a solution where you can actually do both. It's not perfect, but it kind of works, but at horrendous costs. Yeah, you definitely do need some dynamic cast, and from performance perspective, this is definitely a factor of 10, if not even more. And so I would say for dynamic polymorphism, you have to choose. And this is why I actually made the talk. That's, I believe, a pretty important thing to keep in mind.
Okay.
Static polymorphism is different. If you do it right, you can do both. Yeah, if you do not couple things too closely, if you separate your functions, free your functions most of the time, you should be able to do both.
Okay. And I have a follow-up question, which is about the CRTP setup. So I was wondering, what if I want to, the property that I want from the CRTP is to prevent implicit conversion between two derived types, but I don't care about anything else? So imagine, for example, I have multiple integer types in my database, in my code base, and I want to prevent conversion between each other. So I create a base class and I use CRTP to only keep the interface. Is it the best use case?
I hope I get the idea. What you need is a strong type. So you encapsulate your integer,
exactly.
The thing that has this in some other type that does know some other type, and so there is no conversion. So you don't even have to think about CRTP. Interestingly, CRTP often comes up in the discussion of strong types because we often use CRTP to inject functionality into a strong type. But that's a different story. You need
if
a strong
I used
type.
inheritance, my integer type would be double the size, because I would have to, you have virtual. I don't want that. I want everything, So
take a look at strong types, Google for strong types, or perhaps even take a look at strong type libraries. There are a few good libraries around.
Oh, okay, are there? Okay, sure.
Yep.
Thanks very much.
Hi, thank you. I'm trying to wrap my head around how the other patterns, you use the strategy pattern and the factory pattern, fit into this. If you showed your example, without those, would we reach the same conclusions? Are those kind of necessary to reach the conclusions, or just kind of to flesh out the example?
I think it was rather to flesh it out a little bit, to make it a little more realistic. You would arrive at the same problem, but I might not be able to show it as clearly. Yeah, I apologize if this was too much code, but it's not required in order to create this architectural failure.
Okay, thank you.
Yep. Last question.
Yeah, I'll try to express myself and try not to get too turned around. One instance where I felt intuitively at first that I wanted to be able to add new types. I think I'm going to get turned around, but I've felt kind of pushed to use the variant when the thing that would be the interface function is actually the interface-based function would have a template parameter. So we all know how well templates and virtual functions go together or don't go together.
Don't go. Yeah.
So I ended up kind of having to do a variant there. Maybe that's kind of covered under having an open set of operations, because when you write a template function and you wish it could be a virtual function, it feels by the source code that you write like it's one thing, but it's actually maybe many things, right? Because function template is not a function, it's a template
for function. Yeah, exactly.
So I'm not sure if there's an actual question in there. But
we can talk about this later if you want to. Yep, thank you. Good. Enjoy the rest of the conference.